Hi everyone. So we've been describing the Standard Model, how it works, and its huge success. There are some outstanding problems, questions, issues, whatever you want to call it, that are active areas of research for physicists today. And the huge kind of elephant in the room is gravity. Where is gravity? How do we fit that in? That is a huge problem and hasn't been figured out to date. There are a couple other little issues. There's something called neutrino oscillation. And what happens is that when the sun, all the nuclear reactions that are occurring in the sun, these nuclear reactions are pouring out neutrinos. The neutrinos interact only through this weak nuclear force. So they're very difficult to observe. However, people have done that and created huge laboratories to measure the rate at which the neutrinos are flowing through space. And the problem is it's about a third of what it ought to be. So one of the ways that this is explainable is that somehow the neutrinos are actually oscillating between the three generations across the periodic chart. So so that explains the 1/3 nature. And so we can kind of, introduce this idea of neutrino oscillation. It doesn't really fall out of the theory. On the other hand, it's not really incompatible with the theory either. It's just kind of bolted onto the theory in order to explain that situation. And so we have some sort of way in which the neutrinos transform themselves into one another. This also is why they have to have mass. It's the main reason that explains why they are not massless. There's also something called parity violation. The weak force, actually, the way in which the spins of the particles, the quantum spins of the particles, are oriented in any one of these reactions depends on whether or not it's right-handed spin or left-handed spin. That there's a preference for one of these types of spin versus the other. And that violation of parity is called, again, is another feature that can be bolted onto the theory. It's not really incompatible with the Standard Model, but it doesn't fall out naturally. I mean, if we hadn't actually done the experiment, we would have never anticipated including this. And so those are two features that are a part of the Standard Model, but kind of have this feeling of artificialness to them. There's also open questions about the masses of the particle. Why are the particular masses of the particles what they are? Remember, the periodic chart actually does explain the various mass of the atoms through the number of protons and neutrons they have and the various combinations of the isotopes. And so the periodic chart does, the chemical periodic chart does explain the mass of the atoms, but our periodic chart of elementary particles does not. And so that's a weakness. There's also various symmetries. We've talked about how the electroweak force splits into kind of the weak nuclear force and the electromagnetic force. The particular way in which that happens, again, is not really explained. It's something that we look at experiment to tell us how these particles mix together. That's another feature we kind of have to bolt onto the theory. And also, why are there 3 generations? Why are there 6 quarks? Why aren't there just 2? Are there 4 generations of quarks? Are there more to be discovered? This neutrino oscillation kind of gives us the feeling that there really are only 3, but that's an open question as well. So there are significant questions that are open in terms of Standard Model, which is why physicists have speculated there must be a more fundamental theory of everything, if you want to call it something, that's beyond that. And that's what I'd like to talk about in the next upcoming videos. And of course, there's always the elephant in the room, gravity. How do we incorporate gravity into this massive theory of everything.